Hi guys, my name is John Filesticker. I'm the mathematics coordinator at the Broward Teaching Center, and today we're going to go through the problems from the MAC2233, the Survey of Calculus Final Exam Review, specifically the review that was put together for the UF Online students. The first problem on the review looks like this. If f primed is equal to the natural log of x squared divided by x, and f of e is -1, find f of e to the fourth. We're given the derivative of the function. We know we can walk backwards in the differentiation process to the function itself by integrating once. So we'll start with that. We know up to an additive constant, this fact implies f of x is equal to the indefinite integral of log squared x divided by x dx. I'm going to write log squared in place of log. It's just a simplifying, in place of log of x all squared. It's a simplifying notation. It makes life easier, takes up less space on the board. Please don't panic. Log squared just means log of x all squared. How do we do this integral? At first it might look challenging, but once you glance at it for a minute, once you've got a little bit of practice, you'll recognize that the derivative of one of the main pieces of this integrand exists in here already. Namely, if you make the substitution u equals log x, so that du is equal to 1 over x dx, observe that you can rewrite your integral as log squared x times 1 over x dx. So right here, you have your du. Putting everything in from the substitution, log squared is u squared. 1 over x dx is du. So we've converted our integral in x's to an integral exclusively in u's. That's what we need to do to proceed. Now this is just a power rule integral. But because it's indefinite, we know we need to add on a plus c. We don't know what c is yet. Remember, the goal of the problem is to find f of e to the fourth. So we need to figure out what this constant is in order to know what f is for sure. This tells us more or less the shape of f, but it doesn't give us exactly f. It gives us f up to this additive constant. So first we'll go back to our original variable, which was x. Using the substitution we chose, u equals log x. This becomes log cubed x. I'll write that over 3 as a 1/3 out front, plus c. Okay? So we've completed the integration task, but we still don't have everything we need in order to evaluate f of e to the fourth. Namely, we don't know what this constant is. Thankfully, we're given a piece of information that will help us find that constant. Namely, we were told f of e is equal to -1. So this lets me set up the equation. Let's do it like this. I'm just going to make a little partition here so we've got some space to work with. It's clear what goes with what. I know that f of x is equal to this nonsense, so I know that f of e is -1. So -1 equals f of e equals what you get when you plug e in here. Okay? Nothing bad yet. The task now is just to solve for c. It might be useful, since this notation is new. Let's go back to the starting notation so you don't get confused. All right, it's like this. These are just saying the same thing, just changing one notation back to the other. The natural log of e is 1. 1 cubed is 1. 1/3 times 1 is 1/3, so this simplifies to 1/3 plus c, which implies c is equal to -1 minus 1/3, which is -4 over 3. Okay? So now we know exactly what f of x is. Right? We know that f of x is equal to 1/3 log cubed x plus c. c is -4/3. Okay? So this is where we stand. We know everything about f of x. So if you want to know in particular what f of e is, then it suffices just to plug, we're after e to the fourth. If we want to know what f of e to the fourth is, it suffices to plug e to the fourth in here. And again, just to get you used to this new notation, I'm going to walk back to our old notation for a second. Okay? So now the natural log of e to the fourth can use one of our properties of logarithms. Says you've got the log of a to the b is the same as b times the log of a. So this is the same as 4 times ln of e, all cubed, minus 4/3. Log of e is still just 1, so we'll have 4 cubed over 3 minus 4 over 3. And it's up to you how you simplify from here. 4 cubed is 4 times 4 times 4 is 16 times 4 is 64, so that's 64/3 minus 4/3, which is just 60/3. The second problem on the review asks us to calculate the exact area bounded by the function f of x equals 2 over x and the x-axis on the interval 1, 3, so between x equals 1 and x equals 3. I went ahead and sketched the region in question here just to make sure that it's all above the x-axis. Remember that sometimes if you're using an integral to measure area, if the function bounding that area happens to be negative, then any area bounded by a negative portion of that function's graph will be measured with a negative weight by the integral. In this case, it doesn't hurt us, but I think in general it's a good idea to always sketch the region you're playing with before doing any calculation. One of the facts that we've learned this year is that the area bounded by a positive function in the x-axis is always given by the definite integral from the left endpoint to the right endpoint of that interval of the function itself, which in this case is 2 over x dx. We can use the linearity of the integral to pull the factor of 2 out front. And our integral becomes 1 over x dx. And then you remember that 1 over x is the derivative of the natural log. So an antiderivative for 1 over x is ln x, log x. So now the only thing to do is to evaluate, right? We found our antiderivative. We don't need a plus c or anything like that because this is a definite integral, an integral with bounds or an integral with limits. And then to evaluate, we just plug in the upper limit and subtract what we get when we plug in the lower limit. ln1 is of course 0, so this is equal to 2 log 3, or 2 ln 3. And then we can use the power rule for natural logs. And we write this as ln 9, or log 9, natural log of 9 if you like. The third problem is similar in spirit to the second. We're finding area bounded by a function's graph. Okay, as before, I sketched the region. This is important to remember because if you were to just calculate the integral from 0 to 3 of this function, then you'd end up measuring some of the area with negative weight. So in order to make up for that, we're going to slap a negative 1 onto the integral that measures this area. The integral that measures this area we'll leave alone. In other words, if you want to express this area as an integral, it can be done as the integral from 0 up to 2 of our function f of x, which is 4 minus 2x, dx, minus, rather than plus, the integral from 2 to 3 of f of x dx. These are definite integrals. They have different limits. You can't combine them and cancel. We just have to evaluate both. The way to do that is by finding an antiderivative and then taking the difference at each end. It's the fundamental theorem of calculus. I'm sure you all remember that. So an antiderivative for 4 minus 2x is 4x minus x squared. And we'll need to evaluate that guy between 0 and 2. Once we have done that, we will separate, or we'll subtract off this guy's antiderivative evaluated between his endpoints. The antiderivative here is the same. It's 4x minus x squared because it's the same integrand. But now we're evaluating from 2 to 3. So far, nothing bad. If we plug 2 in here, we get 4 times 2, which is 8, minus 2 squared, which is 4, so we get 4. If you plug 0 in, you get 0, so nothing interesting there. Minus. Always use parentheses. When you're not sure, if you stack these parentheses, you'll be less likely to jumble up a negative sign. Just be careful and use them everywhere you think you should. So now here we need to evaluate this guy at 3. If I plug 3 in here, I get 12 minus 9, which is 3. Minus, if I plug the 2 in here, I get 8 minus 4, which is 4. And now we just need to simplify. 4 minus 0 is, of course, 4. Minus 3 minus 4 is negative 1, so this is 4 plus 1 equals 5 square units. Units squared. If I gave each one of these guys, I called a unit. She asked for units, so. And that's it. In the fourth problem, we're asked to evaluate the integral from 0 to 3 of 4 minus 2x, and then to compare that to our answer from the previous problem. Remember, we hinted at the issue in finding areas with functions that are sometimes negative, and this is just to help us get a better grasp on what can go wrong. So if we were to just evaluate this without thinking about geometry at all, without looking for area, we're just given this definite integral and told to evaluate. We know what to do. We use the fundamental theorem of calculus. We find an antiderivative. We've already done that plenty of times. And then we evaluate between 0 and 3. Now if I plug 3 in here, I'll have 4 times 3 is 12, minus 3 squared is 9, minus what we get when we plug in 0, but that's just 0 minus 0. So no contribution from the lower limit. But if you take 12 and 9 there, then you get 3, which is not what we found in the previous problem. So there is a difference, and it's exactly the difference I mentioned at the start of the earlier problem, is that integrals will measure area, but if that area lives below the x-axis, it will measure that area with a negative weight. And since this function goes from being positive to negative on the interval 0, 3, some of the areas measured negatively, some of the areas measured positively. So always remember, if you're looking for an area, sketch the region and make the appropriate sign changes. Problem 5 asks us to find the maxima and the minima for the function f of x equals x times e to the minus x on the closed bounded interval 0, 3. That's an important theorem. It says that any continuous function on a closed bounded interval attains an absolute max and an absolute min. So we're looking for those. Okay? We know that the absolute extrema can either come from local extrema on the internal part of the interval, or from the value of the function at the endpoints, right? And let's just look at a quick picture to see how that might be the case. If I'm on the interval a, b, and I look at some function, maybe like this, you can see that its absolute max on the interval a, b occurs over here, even though this isn't a hump or a hill. It's not the sort of extrema that we're used to finding in this class. And its absolute min maybe occurs here at a local min, or maybe it occurs here. Can be nebulous, so you have to be careful. When you're looking for absolute extrema, remember always find local extrema, and then compare those to the value of the function at the endpoints of the interval. So let's do that for the function we were given. First, we're going to go on a hunt for local extrema. To do that, we need to find the derivative, f prime of x, and in this case, that will require the product rule. Now, the way I remember the product rule is first differentiate one, don't differentiate the other, then differentiate the one, don't differentiate the other. I know it's a silly mnemonic, but it works for me. So first I'll differentiate the x. I'll leave e to the minus x alone, so I get 1 times e to the minus x plus. Now I'll leave the x alone, I'll differentiate e to the minus x, so I'll have x times, now my derivative for e to the minus x is e to the minus x times negative 1 by the chain rule. We can simplify this a little bit. And a little bit further, factoring e to the minus x out in that last step. Okay, now if I'm looking for local extrema, like I said we are at the start, we need to find out where f prime is equal to 0. So I set this bad boy equal to 0. Remember, exponential functions, e to the stuff is never 0. Doesn't matter what the stuff is, even complex numbers. So this thing is only going to be 0 at x equals 1. So the only place I could possibly have any local mins or local max is at x equals 1. But remember, that theorem guarantees the existence of both a min and a max So I know that I need to get something else, and we also know that things can, extrema can come from endpoints. So let's take a look now at, well, before we proceed, before we evaluate the function at the endpoints, let's figure out what f of this is so we know what we're comparing to. Okay, so we'll say x equals 1 is the only possible location of local extrema, and f of 1 is equal to 1 times e to the minus 1, which is just 1 over e. Now, let's look at the endpoints. F of 0 is equal to 0 times e to the minus 0. E to the minus 0 is e to the 0 is just 1, so 0 times 1 is just 0. F of 3 is 3 times e to the minus 3, or 3 over e cubed. So we want to know which of these is smallest, which of these is largest, right? These are all of our possible candidates for local and, or for absolute extrema. We should say local and absolute, but really absolute encompasses all of those. First, note that these two are positive numbers, necessarily larger than 0, right? So you know your absolute min is 0. Next, we want to compare 1 over e and 3 over e cubed. So we ask the question, which is larger? There are a lot of ways to go about this. What I suggest is make a guess. Make a guess and write that guess as an inequality. And then you can play around with that inequality, reduce it to something that's easier to understand. I suspect that 1 over e is larger than 3 over e cubed. So I will say, my guess, 1 over e greater than 3 over e cubed. If I can simplify this to a true statement, then I win. My guess was correct. If I simplify this to a false statement, I still win by learning my guess was wrong. So, how can we simplify this? Well, let's multiply by e cubed on both sides. The e's and e cubed here will give me an e squared on the left. So this reduces to the statement e squared is greater than 3. Is that a true statement? Well, we know e is bigger than 2. We know that 2 squared is 4. So e squared certainly must be bigger than 4, which is bigger than 3. So yes, my original guess was correct. 1 over e is larger than 3 over e cubed. So since we know our absolute min is 0, we know the only other candidates for absolute extrema are 1 over e and 3 over e cubed. My absolute max must be 1 over e. I'm sure there are other ways to do this. This is just the one that's most natural to me. Number 6 is a true or false question. The statement is d dx, the integral from 1 to 2 of f of x dx is equal to 0. Assume that f is continuous. All right? So if f is continuous, I know that this integral exists. In particular, I know that this integral, I write it down here, 1 to 2 f of x dx is a certain kind of object. Okay? Is it a function? Is it a linear map? Is it a Stromboli? Is it a real number? Right? It's a real number, right? You can think of these as measuring area. That's one way to remember that it's a real number. You're integrating a continuous function over an interval, so you know that the output from this thing, whatever this thing is, it's some number. It's some number that represents the area underneath that function if that function is positive, or some combination of weighted areas if that function is capable of changing sign. In particular, it's just some number. It's a constant. So, d dx of this thing is d dx of some constant. I don't know what it is, it's some constant, but remember the derivative of a constant is always 0. So, true, this is equal to 0. I'd like to add a caveat to that last problem, because you guys towards the end of the semester spend a lot of time differentiating integrals and getting really familiar with the fundamental theorem of calculus. One simple modification I could make to this that would make it a non-true statement would be something like this. Okay? So if instead of having a definite integral with known bounds, fixed bounds, remember the original problem said integrate from 1 to 2 f of x dx, differentiate that thing. Here, if I were to integrate from 1 to x and differentiate with respect to x some f of t dt, I'm just using some other variable there so we don't confuse them, then this is not guaranteed to be a true statement, because this thing is no longer a fixed real number. This thing is now a function of x. It depends on the size of the interval, right? If you interpret this as an area, then the area between f and the x-axis depends on how far out you're looking, right? If I look from 1 to 1, it would be 0. If I look from 1 to 2, it might be something else. If I let x run all the way out to some very large number, and f is a positive function, then I would expect this to be a large number. So by having a variable up here as the upper limit, I can ruin the trueness of this statement. Just a subtle thing I wanted to point out so you didn't get confused between this and your similar homework problems. Number 7 is also a true or false question. The statement is, if capital F of x and capital G of x are both antiderivatives for little f of x on some interval, then capital F is equal to capital G. At a glance, we might think this is true. If capital F and capital G both differentiate to become little f, we might suspect that capital F and capital G are the same. In mathematics, when we think something might be true but we don't have any real grounds to stand on, the first thing we do is try to come up with a counterexample. We try to check our intuition. If we're unable to come up with a counterexample, we might start to think that the thing is true and then we'll try to prove it. I think in this case you'll be able to find a counterexample pretty quickly without too much work. Namely, if I let capital F of x be the function 1, capital G of x be the constant function pi, then capital F and capital G are both antiderivatives for the function 0, right? So we'll say if, then capital F prime of x is equal to 0, capital G prime of x is equal to 0. So F and G are both antiderivatives for some little function, in this case the 0 function. But capital F and capital G are not equal. 1 is not equal to pi. In general, the relationship here, the relationship between two functions who have the same derivative, or two functions that are the antiderivative for the same guy, means that they're just vertical translations of one another. Right? There are a lot of other counterexamples. This is where our plus c comes from when we do indefinite integrals. You could take x squared and x squared plus 5. Those will both have the same derivative. Right? Lots and lots of examples. Examples abound. There are infinitely many, but I think this is the easiest one. Two constant functions, different constant functions, both differentiate to 0, but are not equal to each other. In fact, anywhere. Question number 8 is true-false again. We're asked to evaluate the statement d dx f of x dx is equal to f of x. We want to know, is that a true statement or is that a false statement? We know that integration and differentiation undo each other just with some caveats. So let's explore this a little bit. Suppose little f has antiderivative capital F. In other words, suppose capital F prime is equal to little f of x. Then, in other words, capital F is an antiderivative for little x. Then the indefinite integral of little f dx is equal to capital F of x plus c, right? So we can take this piece and put it in here and see if what we get out is little f of x. So the statement, let me give this a name. So substituting what? Substituting 2 into 1, we see d dx of this integral, which I know is just f of x, capital F of x plus c, equals little f of x. We want to know, is this a true statement? But now d dx of capital F of x plus c is equal to f primed of x plus 0. And f primed of x, by definition, as an antiderivative, is equal to little f of x. So yes, those are equal. This is a true statement. Number 9 is again true, false. I switched to blue here, my black marker was dying, sorry if blue bothers you. The statement we're asked to evaluate the truth of is if f of 3 is equal to negative 4, f primed is continuous, and the integral from 3 to 6 of f primed of x dx equals 8, then f of 6 equals 4. The best way to figure this out is to kind of unpack the different statements. So the important things for us calculation-wise are this fact and this fact. We're told that f primed is continuous to make sure that this integral exists. How can we do this? Well, you know that if you were handed this integral, right, not equal to 8, but just this integral, and asked to evaluate it, the trick would be to find an antiderivative for the thing inside and evaluate between endpoints. We know an antiderivative for f primed is f, so let's begin with that. The integral from 3 to 6 of f primed of x dx, well, on the one hand I know it's 8, so I'll write the 8 over here. On the other hand, I know that this is equal to f of 6 minus f of 3. Why? Because f is an antiderivative for f primed, by definition. Now, we were given some other information, namely that f of 3 is negative 4. So this is equal to f of 6 minus negative 4. Okay, or we can rewrite that if you like. F of 6 plus 4. So it might seem at the outset that we weren't given enough information to resolve this, but in fact you were. Just using the fundamental theorem of calculus and the little bits of details that they gave you, we can sort this out. We have f of 6 plus 4 equals 8. That is a consequence of these things. So, subtracting 4 from both sides, we find that f of 6 is equal to 8 minus 4, or just 4, which is what they asked us about. So indeed, this is a true statement. These three things combine to imply this, because the fundamental theorem of calculus. We're moving on now to part 2 of the review, so the numbers start counting back over. We'll start with number 1. Number 1 is a problem in many parts. Each one is a definite integral. The first part, part A, is the definite integral from 3 to 8 of 3x divided by x squared minus 4 dx. Looking at this for a minute, you realize it's a good candidate for substitution because the derivative of the bottom is a constant multiple of the top. So let's go with that. I will let u equal x squared minus 4 so that du is 2x dx. Also, since this is a definite integral, when I make a substitution, I'd like to change the limits of the integral in order to avoid having to go back to my original variable. So, observe that when x is equal to 3, u is equal to 3 squared minus 4. That's 9 minus 4. So the old lower limit, 3, goes to the new lower limit, 5. Similarly, the old upper limit is 8, so when x is equal to 8, we know that u is equal to 8 squared minus 4. That's 64 minus 4. So my old upper limit, 8, will go to a new upper limit, 60. Okay, so that's all the information involved in our substitution. We can plug everything in. I'll rewrite the problem here, bringing the 3 out front just to make it more clear to see how the substitution is going to go in. X dx is equal to 1/2 du. So this piece can be replaced by 1/2 du. So my integral becomes 3/2. The integral from 5 to 60 du over u. Antiderivative is just log u, or natural log u. So I've still got my 3/2. And now I have the natural log of u being evaluated between 5 and 60. From here, it's just a matter of calculation. This is 3/2 times the natural log of 60 minus the natural log of 5. We can use properties of logarithms to combine those two pieces. So this is 3/2 times the log of 60 over 5. 60 is 6 times 10, so this is 6 times 10 divided by 5 is 6 times 2. So this is 3/2 times the natural log of 12. We're looking now at part B of problem 1 of part 2 of the final exam review for Survey of Calc 1 UF Online students. It's again an integral. We're asked to evaluate the indefinite integral of e to the 4x minus e to the x over e to the 2x. You might be tempted by a substitution here, but there's actually something cleaner you can do, at least to start with. I always suggest try any algebra you can. Notice if you split this integral up into two pieces, it becomes nicer. E to the 4x minus e to the x over e to the 2x is the same thing as e to the 2x minus e to the x over e to the 2x, which is e to the negative x. So this is e to the plus 2x minus e to the minus x dx. Okay, now from here, each of those pieces is easy to evaluate with a little substitution. So we'll split the integral into two separate pieces. And eventually you'll get to a place where you don't need substitutions to solve things like these. You'll be able to see what the antiderivative is right away, because there's a general form for all functions like e to the bx. But we'll go ahead and do it the long way until we get used to it. So in this first integral, I'll let u equal 2x, so that du is 2 dx. And this tells me that dx is 1/2 du. So my first integral becomes 1/2 integral e to the u du. And in my second integral, I'll let z equal negative x, so that dz is equal to negative dx. And now my integral becomes negative, so this becomes plus e to the z dz. I'm choosing to use different letters there in each integral because I don't want to be tempted to combine them again afterwards. If I were to use u here and then stick them back together, u means different things in those guys. So it wouldn't be appropriate, even though the notation would suggest that it is. So get comfortable using different letters for your substitutions, especially if you're going to be using multiple substitutions in one problem or successive substitutions. It's a good idea. Now each of these are very simple, straightforward exponentials. They have their own derivative, hence their own antiderivative. So this first guy becomes 1/2 e to the u plus c. The second guy becomes just e to the z plus c2, c prime, say, doesn't really matter. And then we can put everything back into the original variable, which in this case was x. So u is 2x, so this is 1/2 e to the 2x plus c, plus z is negative x, so this is e to the minus x plus c prime. And now I'll just group things together in a way that's more reasonable. Namely, I'm going to put the constants together. So I get 1/2 e to the 2x plus e to the minus x. And then c plus c prime, well, if those are arbitrary constants, then their sum is an arbitrary constant, so I'll just say plus capital C. Okay? So the important thing here is to recognize that you can do some algebra to make your life easier, and then separate substitutions. Making sure to use different labels for each of the substitutions so that you're not tempted to recombine things that oughtn't to be recombined. Then just evaluate as normal. Part C of problem 1 is the definite integral from 1 to e of 1 plus 2 log x all squared divided by x dx. Again, by now, hopefully you're getting comfortable with substitutions. You can spot when one is useful. In this case, observe that the derivative of this piece, right, inside the square, is a constant multiple of 1 over x. So the correct substitution, just for fun, I'm going to use a new letter. Let's use z, equals 1 plus 2 log x. So dz is just 2 over x dx. Okay? Or you could write this as 2 times 1 over x times dx, if that makes you happier. So you've got a 1 over x from this guy, your dx is here. What you don't have is a 2. So if you divide everything by 2, you get 1/2 dz is equal to that. So my integral is going to look something like this. This piece is just z, so my top becomes z squared. 1 over x dx is almost exactly dz, except for a factor of 2. So that's how our integral transforms. We'd also like to change the limits. We mentioned in an earlier problem that when you're making a substitution in a definite integral, it's good to get in the habit of changing your limits so you don't have to go back to the original variable at the end to evaluate. So, if x is equal to 1, then z is equal to 1 plus 2 times the log of 1. The log of 1 is 0. 2 times 0 is 0. So 1 is fixed, right? If x is 1, so is z. If x is equal to e, then z is equal to 1 plus 2 times the log of e. The log of e is 1. 2 times 1 is 2. 1 plus 2 is 3. So e goes to 3. So my old integral went from 1 to e. My new integral will go from 1 to 3. Sounds kind of cute, doesn't it? Okay, now all we have to do is evaluate. I'll bring out my 1/2. And now I'll use the power rule to evaluate find an antiderivative for z squared. And evaluate between endpoints. Of course, z squared has antiderivative z cubed over 3. I can lump my constant factors out front as 1/6. And then I've got z cubed evaluated between 1 and 3. That's 1/6 times 3 cubed is 27. Minus 1 cubed is 1. So this is 26 over 6. Those both have common factors of 2. So if you like, you could write that as 13 over 3, and life doesn't get any better. They're both prime. For part D, we're asked to evaluate the integral from 2 to 5 of x divided by the square root of x minus 1 dx. Again, it might look tricky. We're going to use a substitution here, and we're going to use it a little bit differently than we have previously. In particular, the differential term isn't what's going to clean things up for us. So I'll just show you what came to mind when I saw this problem. I'd like to make the substitution u equals x minus 1, because it's that square root down there that makes things feel wonky. Of course, that just means du is equal to dx, so no savior from the differential, but there is something else that happens. As a consequence of this substitution, I get that x is equal to u plus 1. Okay? So just hold on to that, keep that in mind. Because this is a definite integral, and we're making a substitution, we're going to change our limits. When x is equal to 2, u is equal to 2 minus 1. So the old lower limit, 2, goes to 1, and the upper limit, 5, goes to 4. So this integral, under that substitution, becomes the integral from 1 to 4. Downstairs, I just have the square root of u. Upstairs, I have x. Now my differential term isn't going to clean this up. X dx isn't going to save me anywhere. But I've got x equals u plus 1 as a consequence of my substitution. So we're going to kind of go backwards here, and we're going to use that to replace this x by something involving u. Remember, we always need to have just one variable when we're evaluating an integral. You can't have u's and x's floating around. That's not allowed. So if I replace this x by what it is in terms of u, namely u plus 1, then I can finish rewriting my integral like that. You might say, I haven't done anything. This doesn't look any better. But now I can split this ratio up across its numerator. So I have the integral from 1 to 4 of u over the square root of u, du, plus the integral from 1 to 4 of 1 over the square root of u, du. And now hopefully you see that this is the right path. This will do the job. Each of those just becomes a power rule integral. U over square root of u is just u to the 1/2. And then 1 over the square root of u is u to the negative 1/2. I'm leaving off my du's there, I shouldn't do that. There we go. All right, incrementing the power by 1, dividing by the new power, I get u to the 3/2 divided by 3/2. So that's 2/3 u to the 3/2, evaluated between 1 and 4, plus, and here I'll have u to the 1/2 divided by 1/2. So 2 times u to the 1/2, evaluated between 1 and 4. At 4, here I'll have 2/3 times 4 to the 3/2 The square root of 4 is 2, cubed is 8, so I'll have 2/3 times 8. So I'm going to use some parentheses here to make sure I don't mess up. It's a multiplication. Minus what I get when I plug in 1. 1 to the 3 halves is just 1, so this is minus 2/3. Plus, here if I evaluate this guy, I guess I can get rid of this. If I evaluate this guy at 4, I've got 2 times 4 to the 1/2 is 2 times 2 is 4. Minus 2 times 1 to the 1/2 is just 2. So there's your daddy. This guy I'll factor 2/3 out of to make it easier to simplify. So this is 2/3 times 8 minus 1 plus 4 minus 2 is 2. So that's 2/3 times 7 plus 2. And whether you want to leave it like that or combine is up to you. Let's combine these, that's the right spirit. So 2 times 7 is 14, so that's 14/3. And if I want to write 2 as a ratio over 3, that's going to be 6. So altogether, I've got 20/3. So the trick here is a common one, and it's one that throws a lot of people off. Intuitively, what I do is I see that it's the square root downstairs that's making life hard. If I could get rid of that, that would be nice. Or if I could even reduce the thing inside the square root to a single variable, that would be nice. So I know it's at least worth trying to make this substitution. Now, if you make that substitution blindly and you just get the square root of u and x dx upstairs, you might say x du, because du and dx are the same thing. You might ask, how can I make this work? It doesn't appear to work. But always remember that you can solve this for the original variable in times of desperation. And when you feel panicked, when you feel like what you're doing isn't working, you are in a moment of desperation. So in this case, doing that and just plugging in, everything follows nicely. It won't always, but it's an important trick, and it's one that you should get used to. Part E of problem 1 in part 2 of the review asks us to evaluate the definite integral from 0 to 4 of the square root of 3x plus 4. Hopefully everybody can see this one right away. The substitution should be u equals 3x plus 4. So du is 3 dx. Our limits of integration are going to change because we're making a substitution in a definite integral. We've talked about that a few times now. So my old limit, 0, when x is 0, u is 3 times 0 plus 4, so 0 goes to 4. My old upper limit was 4, so when x is 4, u is 3 times 4 is 12 plus 4 is 16. And now we can carry everything out. So this integral becomes the integral from 4 to 16 of the square root of u times du over 3, if you like. Right? Dx is 1/3 du. I can pull that 1/3 out front, still integrating from 4 to 16, root u du now. And this is just a power rule integral. We did a couple of these in the last problem. So that's u to the 1/2. It's going to integrate to u to the 3 halves divided by 3 halves, which is 2/3 times u to the 3 halves. So with 1/3 out front, this becomes 2/9 u to the 3 halves evaluated between 4 and 16. I'm going to leave my 2/9 factor out front when I do my evaluation. If I plug 16 in, 16 to the 3 halves, well, I need to take the square root and then cube it. The square root of 16 is 4. 4 cubed is 64. So this is 64 minus. If I take 4 and I plug it in here, the square root of 4 is 2. 2 cubed is 8. So this is 64 minus 8. So altogether I have 2/9 times 64 minus 8 is 56. 56 is divisible by 9, so you can simplify that if you like. I'm not going to. The final piece of problem 1 of the second part of the review is the definite integral from 0 to 3 x e to the 3x squared dx. I want to take a quick minute to talk about notation. Anytime you see e to the x squared, you might be tempted to ask, is that the same thing as e to the x squared, question mark, question mark. Because notationally they appear similar. If I were to omit these parentheses, you wouldn't be able to tell at all. But you know that this guy is e to the x times e to the x, which is e to the 2x from our rules for exponents. So just know that anytime you see something like e to the x squared, we mean e to the x squared, not e to the x squared, which we would always just rewrite as e to the 2x. Okay? With that in mind, we'll move on. In general, things like e to the x squared are difficult to integrate. It's hard to find an antiderivative for them. But in our case, we have this little guy to help out. Notice that this guy is a constant multiple of the derivative of the exponent here. So if I make a substitution, let's say z equals 3x squared, then dz will be 6x dx. So this x dx is a constant multiple of dz, means we can make this substitution go. Before we plug everything in, I'd like to see what our limits are doing under this substitution. When x is 0, z is also 0. When x is 3, z is 3 times 3 squared. That's 3 cubed is 27. So 3 goes to 27. So my old integral ran from 0 to 3. My new integral will run from 0 to 27. And let's see what we have. This exponential piece, e to the 3x squared, just becomes e to the z. X dx is 1/6 of dz. So I've got 1/6 dz. Okay? So that's everything we need to do in our substitution. Now it's just a matter of evaluating this beast. We know that an antiderivative for e to the z dz is just e to the z. So this whole thing is just 1/6 e to the z from 0 to 27. And of course that's 1/6 times e to the 27 minus e to the 0. But nobody would leave it like that since e to the 0 is just 1. So this is 1/6 times e to the 27 minus 1. And that's it. The second problem in part 2 of the review is a word problem. I'm not going to write every word on the board, just the crucial pieces. I'll read to you the problem. The problem states, it is estimated that humans are consuming zinc at the rate r prime of t equals 15 times e to the 0.06 t metric million tons per year, with t equals 0 in 2012. I should add that. T equals 0 corresponds to 2012. It's a two-part problem. In part A, we're asked how much zinc was consumed between 2012 and 2014. That is, when t goes from 0 to 2. In order to find that out, we'll integrate this fellow. So the amount, I should say part A, amount of zinc consumed from 2012 to 2014 is given by, we'd like to add up the amount of zinc that's consumed at each moment between those. And since this represents the instantaneous consumption, we can get that by integrating. Now the t values that are associated with these years, 2012 is 0. If I want to walk 2 years into the future to 2014, that means I need to integrate from 0 to 2. This fellow. dt. Okay, now this is just an exponential integral. We've seen what these look like. Let me pull my 15 out front. Integral from 0 to 2, e to the 0.06 t dt remaining. We can make a little substitution in here, but at this point I'd like to get to that place where we can integrate exponentials quickly. So e to the ax, you know its derivative is always a e to the ax. Its antiderivative is always e to the ax over a. So your antiderivative for e to the 0.06 t dt, bring my 15 along for the ride, is e to the 0.06 t divided by 0.06. Okay? And now we need to evaluate this between 0 and 2. I'm omitting the step of substitution because for functions that are this nice, we ought to just know the antiderivatives. So maybe off to the side here I'll make a note. For all a not equal to 0, the antiderivative of e to the at dt is equal to e to the at over a plus c. Okay? I'm not adding a constant here because this is a definite integral. Let's figure out what this number is. If I evaluate, I can bring my constants outside, and this will be e to the 0.06 times 2 minus e to the 0.06 times 0 is just e to the 0 is 1. Okay, so that's it. That's the amount of zinc that was consumed from 2012 to 2014 under this model. Part B will be in the next video. We're looking now at part B of problem 2. In part 2 of the MAC2233 final exam review, I'll remind you of the context. We were told it is estimated that humans are consuming zinc at a rate of r primed of t equals 15 times e to the 0.06 t, where t equals 0 is, t is measured in years and t equals 0 corresponds to 2012. In part A, we found out how much zinc was consumed from 2012 to 2014 by integrating r primed from 0 to 2. In part B, we're told if there are 10 million metric tons of zinc were consumed in 2012, to find a formula for r. Now, we know that r is the antiderivative of r primed of t, which is the antiderivative of 15, sorry, it's an ugly 5, times e to the 0.06 t dt. Earlier, we discussed how to integrate things like that, how to integrate exponentials of that form. So that's 15 times e to the 0.06 t divided by 0.06, and I've worked out some arithmetic over here also, plus c. So 0.06 is the same as 6 over 100, is the same as 3 over 50. So this is 15 times e to the 0.06 t divided by 3 over 50 plus c. So that's 15 times 50 over 3 times e to the 0.06 t plus c. Now 15 divided by 3 is 5 times 50 is 250. So we get 250 e to the 0.06 t plus c. In order to get an exact formula for r, we need to determine the constant c. Thankfully, we were told that 10 million metric tons were consumed in 2012. 10 million tons being consumed in 2012 is equivalent to saying 10 is equal to r of 0. And by this formula, r of 0 is equal to 250 times e to the 0, which is 1, plus c. Therefore, c is equal to negative 240. Hence, our formula implies r of t is equal to 15 times, r of t is equal to 250 times e to the 0.06 t minus 240. And that's it, we win. Moving on to the third problem of part 2 in this review, we're told to sketch the region bounded by the piecewise function f of x equals x plus 1 for x less than or equal to 0, e to the x over 2 for x greater than 0 on the interval negative 1 to 2, and then to find its exact area. So sketching piecewise functions is something that everybody should get used to doing. We know that for x positive, this thing looks like an exponential function. It's not e to the x, it's e to the x over 2. So it's been scaled a little bit, but it still looks a lot like e to the x. Okay, it just grows a little bit more slowly. So you know at 0, for example, that guy would be 0, but we're only going to start with, that guy would be 1. We're only going to look at things strictly larger than that, though. So this piece of the function looks like that. X plus 1 is a linear function. It has slope 1 and y-intercept 1. So that guy looks like this, and with slope 1, looks like that. This is 1, negative 1. And so that's what the graph of the function looks like. If I'm interested in the area bounded between negative 1 and 2, then I'm interested in this piece. And say 2 Well, where is 2 going to be? 2 is going to be right at E. So if that's 1, a little bit further, say here. So this is the point 2 comma E. And the shaded area is the region in question. If I want to find the area, it's sufficient to integrate f of x from -1 to 2 because this function's positive on that interval. So in order to show you guys a little bit of what graphing and integrating piecewise functions looks like, I'm going to start out by writing it in the abstract. Okay? So it's sufficient to calculate the integral from -1 to 2 of f of x dx. The trouble comes in trying to actually compute that because this is a piecewise function. But have no fear. The trick for integrating piecewise functions is just to remember that for x less than 0, we treat it like this. For x greater than 0, we treat it like this. So we'll split the integral at 0 from -1 to 0. Everywhere on that interval, -1 to 0, the thing looks like x plus 1. And from 0 to 2, the thing looks like e to the x over 2. Okay, so now it's our task just to compute these guys. The first integral follows from the power rule. And the second integral follows from that rule I had on the corner of the board a minute ago. I'm going to put it back here. It's so important. I'd like you guys to all remember this. Antiderivative of e to the ax dx is always e to the ax over a plus c. This is one of those. This is the same as e to the 1/2 times x. So a is equal to 1/2. You can follow this recipe. Okay, so I know that this guy is going to look like e to the 1/2 x divided by 1/2, which is multiplying by 2. And he gets evaluated between 0 and 2. All right, we can use some parentheses to make clear who's being evaluated where. Never forget that. Don't confuse them. At the upper limit, this thing contributes nothing, right? If I plug 0 in, I get nothing interesting out. If I get 0 out. So I've got 0 minus whatever I get when I plug in -1. -1 squared is 1, so I've got my 1/2 plus -1. That's everything from the first integral. I'm going to pull the 2 out before I evaluate this other piece, but it's not difficult either. So I've got e to the 1/2 times 2 is e to the 1, minus e to the 1/2 times 0 is e to the 0 is 1. So that's our daddy. 1/2 minus 1 is -1/2. Negative 1/2 is 1/2, so this whole first piece just becomes 1/2. This second piece is just 2e. And that's it. Let's talk a minute about Riemann sums. I want to talk about them in the abstract before I solve the next problem, which is approximation of an integral by Riemann sums. Okay, if I have the graph of some function f of x, and I'm looking on the interval ab, before we had any notation for integration or any interpretation of integrals as sums, we had the question of finding areas under curves. Some curves are easy, like linear curves, and even quadratic curves can be handled without too much difficulty, but when we want to do them in general, we developed calculus. Riemann was one of the first people to formalize ways to find areas under curves, and what he did is he said, I'd like to take this interval and chop it up into equal length pieces. Now if you've got the interval from a to b, it's of length b minus a, so if I want to chop it up into 2 equal length pieces, it's going to be that length divided by 2. If I want to chop it up into 3 equal length pieces, each piece is going to be that length divided by 3. If I want to chop it up into n equal length pieces, then each one of these guys, for which we use the terminology delta x, is going to be the length of the interval divided by the number of subintervals. So this is the first subinterval, this is the second, that's the third. This would be the nth subinterval. So each one has length b minus a over n. The curve is smooth. It's not made up of straight lines, but we can approximate it by things made up of straight lines, e.g. rectangles. You can also use trapezoids. As I've sketched it, these look like right endpoint approximations. So we determine the height of each rectangle by the value of the function at the right endpoint of each subinterval. So the height of this rectangle is f of this value. Now what is that value? I need to walk one subinterval's width to the right of a. So that's a plus 1 delta x. Similarly, this guy has height f of a plus 1, 2 delta x. We can continue to play those games. This guy would have height f of a plus 3 delta x. That's for right-hand endpoint approximation. The problem we're going to solve in a minute asks for midpoint approximations. So I'm going to draw a picture with less stuff in it, but more detail. Suppose this is just one of my subintervals. Let's not do that. All right? So out here I've got more stuff, out here I've got more stuff. This is a plus I delta x for some I. This guy is a plus I plus 1 delta x for some I. In the example I showed you a minute ago, we were determining the height of the rectangle that I would use to approximate the area under this portion of the curve by the right endpoint. You could just as easily use the left endpoint. The problem we're going to solve in a minute asks us to use the midpoint of each subinterval. Okay? So the midpoint between these two guys is exactly the sum of them divided by 2. So this would be a plus I delta x plus a plus I plus 1 delta x over 2. Right, that's this guy. That's 2a, and then 2I plus 1 delta x over 2. So that's a plus 2I plus 1 over 2 delta x. So that's how, using midpoint approximation, or when working with a midpoint approximation, we find the height of each rectangle. The height of each rectangle will be this evaluated at f, or by f. So the height here is f of a plus 2I plus 1 over 2 copies of delta x. Okay? So if we wanted to know the area under the whole graph, or a good approximation, using midpoints, we would multiply each of these guys, each of these heights, by delta x, and then sum them from I equals 1 to n. Okay? That will give us a reasonable approximation. Midpoint approximation isn't always the best. Sometimes left endpoint is better, sometimes right endpoint is better, sometimes we do other tricks like trapezoidal approximation. But for our purposes, in this next problem, this is the stuff we will need to use. Now we're going to look at problem 4 of part 2 of the MAC2233 final exam review for UF Online students. This is really a problem in 2 parts. They ask us to approximate the integral from 1 to 5 of 2x minus 1, square root of 2x minus 1 dx using midpoint Riemann sums with 4 subintervals. And they also ask us to calculate the exact value of that integral and then to compare the two. The easier of those 2 tasks is to compute the integral directly, so let's go ahead and do that. We'll store it and then we'll compare it to the result we get when we use the Riemann sums. The integral from 1 to 5, square root 2x minus 1 dx is a simple u substitution. We'll let u equal 2x minus 1 so that du is 2 dx. Our limits are going to change. When x is equal to 1, u is equal to 2 times 1 minus 1, which is also 1. So 1 goes to 1. When x is equal to 5, u is equal to 2 times 5 minus 1 is 9. so 5 goes to 9. Thus, under this substitution, our integral becomes the integral from 1 to 9, the square root of u times 1/2 du, which is 1/2 times the integral from 1 to 9, u to the 1/2 du. Now this is just a power rule integral, so this is 1/2 times u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. Evaluated between 1 and 9, you can cancel your 2's, and we get 1/3 times 9 to the 3/2 minus 1 to the 3/2. And now that is 1/3. 9 to the 3/2 isn't that bad, right? Because 9's a perfect square. So the square root of 9 is 3, and then if we cube that, we get 27. 1 raised to the 3/2 is just 1. So this is 1/3 times 26. Or 13 over, no, nothing nice happens there, right? 26 isn't divisible by 3. Okay. So we know that this is what we expect, 26/3. I'll save that off to the side. And in the next part, we'll compute the midpoint approximation using Riemann sums. First, let's graph this function. Always helps to have a nice picture. We're looking on the interval 1 to 5. The square root of 2x minus 1 can be understood as 2 times the square root of x minus 1/2, which could also be understood as the square root of 2 times the square root of x minus 1/2, but that's not especially useful. What we know is that this thing has the shape of the square rooting function dragged to the left or dragged to the right by 1/2 and scaled horizontally by 2. So let me mark this as 1/2, and we know that that's about the shape. Okay? Now, I'm interested in looking from 1 to 5, and I want to use 4 subintervals of equal length. So if I'm going to split the interval 1, 5 up into 4 subintervals of equal length, first we need to figure out the width of each subinterval. So in this case, n is equal to 4. Delta x is always b minus a over n, so that's 5 minus 1 over 4 is 1. So my sum intervals look like 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Okay? Now we want to draw some rectangles in here, because we know these Riemann sums are always computed as sums of areas of rectangles. So, the midpoint between 1 and 2 is 3/2, 1 and 1/2. For now, I'm just going to draw these in. We'll do the computation in a second. The midpoint between 2 and 3 is 5/2, or 2.5. So you see I'm determining the height of my rectangles by the value of the function at the midpoint of each subinterval. This is important. We've got 7/2, and then we have 9/2 here. Notice that because this function is increasing, this midpoint Riemann sum overestimates on the left-hand side and underestimates on the right-hand side. So it looks like the error in each subinterval comes close to canceling out. So we might hope that this is a good approximation. Let me write down what each of these midpoints were. That was 3/2, this is 5/2, this is 7/2, and this is 9/2. Okay, so the height of my first rectangle is f of 3/2. The height of my second rectangle is f of 5/2, and so on. The width of each subinterval is 1, and so the area in these rectangles, not necessarily the area under the graph, but an approximation to that area, is given by multiplying each of the heights by their width and then adding up. So the area of this first rectangle is delta x times f of 3/2. Now we know delta x is 1. I'll write a 1 there to emphasize that it's there. Plus, now the area of the second rectangle, that's f of 5/2 times 1. The area of the third rectangle is f of 7/2 times 1. And the area of the last rectangle there is f of 9/2 times 1. So I'll say my area is approximately equal to this. There it is. That is your Riemann sum using subintervals of equal length, 4 of them, and the midpoint rule. In order to figure out what this thing is, it's sufficient to calculate these numbers and add them up. Let's do it. F of 3/2 is the square root of 2 times 3/2 minus 1. So I'll try to squeeze this in here. The ones I'm going to ignore because we know they go away. So the second guy is the square root of 2 times 5/2 minus 1. This is the square root of 2 times 7/2 minus 1. And this is the square root of 2 times 9/2 minus 1. Okay? We can further simplify this. The 2's are going to cancel in each of these. So this is the square root of 3 minus 1. Plus the square root of 5 minus 1. Plus the square root of 7 minus 1. Plus the square root of 9 minus 1. That's the square root of 2, plus the square root of 4, plus the square root of 6, plus the square root of 8. Some of those are nice, but not all of them, right? In fact, most of these are pretty nasty. But this is root 2 plus 2 plus root 3 times root 2. I don't know if it's nicer to write it that way or not. No, I won't. Plus 2 square roots of 2. And my hope is here to clean this up into an integer plus an integer multiple of the square root of 2, but that can't be done because of the 6. So you could say this is 2 plus 1, 2, 3 copies of the square root of 2, plus the square root of 6, which is square root of 3, square root of 2. So if you really want to be picky, this is 2 plus the square root of 2 times 3 plus the square root of 3 in parentheses. Now, I don't know exactly what that is, but I can approximate it for you using a calculator. And it turns out that that's about 8.7. Now 26 over 3, should be pretty close to that as well, right? Because 24 is divisible by 8. While I'm here, let's get a decimal approximation for that. It's 8.66666. So 8.67, 8.7, we're within a tenth. So this is a very good approximation. These techniques aren't that bad if you get used to them. I know the notation is scary with all the capital sigmas, but just remember that capital sigma just means add these things up. Each of those pieces can be made sense of, and then that will allow you to make sense of the whole. So take your time, make sure you know the definitions and the notation, and there's no reason to ever be afraid of these problems. All right, guys, next we're going to look at number 5. Problem 5 from part 2 of MAC2233's final exam review for UF Online students. It's an indefinite integral. We're asked to integrate the square of root x minus 2 over root x. And while your first thought might be to substitute something like u equals the square root of x, if you actually carry out the algebra, this simplifies a little bit. So if you just square out that integrand, you'll be able to see a much quicker way of handling things. So if you square this out, you'll have this squared minus this times this twice. Plus this squared. And you can see already that this is going to be quite nice. We're assuming implicitly here that x is at least 0, so we can cancel, and everything becomes as nice as it could be. And then you know how to integrate each of these pieces individually. Always remembering to add your constant. Okay guys, moving on to problem 6. This is similar to the fourth problem where we're given an integral, a definite integral, in this case the integral from 0 to 2 of x over x squared plus 1 dx. And we're told to approximate it with a Riemann sum and to compute it exactly. This time instead of using the midpoint Riemann sums, we're going to use the right endpoint Riemann sums. But it's essentially the same task. We just determine the height of our rectangles by the right endpoint of each subinterval instead of by the midpoint or the left endpoint. As before, computing the integral exactly is a little bit quicker and takes up less board space. So I'm going to do that first. We'll do part B first, and then we'll come back and do part A. I want to compute 0 to 2, the integral from 0 to 2, x over x squared plus 1 dx. As in a bunch of other examples we've seen so far, the nice thing to notice here is that the top is a constant multiple of the derivative of the bottom, so a u substitution will handle this. If we let u equal x squared plus 1, du is 2x dx. Also, our limits are going to change, as we've always discussed with these. So if x is 0, then u is 0 squared plus 1. If x is 2, then u is 2 squared plus 1. Okay, so that's the information we need for our substitution. Under that substitution, this integral becomes the integral from 1 to 5. X dx is 1/2 of du, so I'll pull a 1/2 out front. And x squared plus 1 is just u. Okay? So that's our substitution done. And now we have 1 over u du. An antiderivative for that is the natural log of u, which we must evaluate between u equals 1 and u equals 5. I'll leave my 1/2 out front. We get the natural log of 5 minus the natural log of 1. But log 1 is 0, so this is 1/2 log 5, or log square root of 5 if you prefer. Okay? Next, we're going to compute, or we're going to approximate this integral. We're going to approximate that area by computing the integral with right endpoint Riemann sums using 4 subintervals of 0, 2. So I'm going to erase this work. Remember part B, we got 1/2 log 5, or log square root 5. So let me store that off to the side. Say exact value. And as before, I'll compute this as a decimal using a tool so we can compare the two at the end. Okay? So now to this task. As before, I think it's illustrative to look at a picture. Now this function is sufficiently well known, at least to me, that I can tell you it looks a little bit like that. For positive x, it's an odd function, it looks similar over here. We're interested in the interval 0, 2, so let me go ahead and mark this off as 2, and I need to subdivide this into 4 pieces. So my delta x is always b minus a over n, in this case is 2 minus 0 over 4, is 1/2. That means in order to get from the left endpoint of one interval to the left endpoint of the next interval, I need to move over 1/2. In other words, my intervals are of width 1/2. So starting at 0, my first right endpoint is 1/2. I mark 1/2 further down at 1 to get my next. 1 and 1/2, or 3/2, will be the third. And then the right endpoint is the one that we already have here. Okay? So what are my rectangles going to look like? Well, if I'm using the right endpoint rule, then I know there's a rectangle associated with the interval 0 to 1/2. So I will look where the right endpoint of that interval intersects the graph of my function. That will determine the height of that rectangle. And I'll draw the vertical pieces in. Similarly here, the right endpoint of my second subinterval, which is 1, will determine the height of my second rectangle. And likewise. Okay, so it looks like these guys are overestimating a little bit, and these guys are underestimating. This guy looks like he's underestimating a lot, but that could be my picture. Let's figure out exactly what those heights are, right? So the height of this rectangle, since that point lives on the graph, this is 1/2 comma f of 1/2. In other words, this height is f of 1/2, where f of x is this function. X over x squared plus 1. Okay, similarly, this is f of 1. The height here, this point is 3/2 comma f 3/2. And this is 2 comma f of 2. Okay? So the width of my first rectangle is 1/2. The height of my first rectangle is f of 1/2. We can start writing down what the Riemann sum itself actually is. So our integral, 0 to 2, f of x dx, is approximately equal to 1/2 times f of 1/2. This is my width, this is my height, plus 1/2 f of 3/2 plus 1/2, sorry, at 1/2, this guy should be f of 1. This is f of 3/2. And then finally plus 1/2 f of 2. And we can factor from that 1/2 to make our lives easier and figure out what each of these guys are. If f of x is equal to this, then f of 1/2 is equal to 1/2 divided by 1/2 squared plus 1. That's 1/2 times 1 over 1/4 plus 1. 1 I can write as 4/4. So downstairs I have 5/4. The reciprocal of that is 4/5. Simplifying, I get 2/5. Okay, so this first piece here, f of 1/2, is 2/5. Next I'll compute f of 1. That's 1 over 1 squared plus 1 is just 1/2. Next we need f of 3/2. That's 3/2 divided by 3/2 squared plus 1, which is 3/2 times. 3/2 squared is 9/4 plus 1, so this is 1 over 9/4 plus 1. 1 can be written as 4/4, so that's 10/4. So when we take the reciprocal, it is 4/10. So it's 3/2 times 4 over 10. And we can cancel the 2's out of the 4 and the 2 downstairs here. So this will become 6/10. No, I'm sorry. What's the nice thing to do here? We can cancel more than that, right? So we can cancel, let's do this in steps. It's early for me, guys. Okay, so I can cancel 4/5 to 4/10 to 2/5, and then the 2's go, so I get 3/5. Always worthwhile to slow down and take a second to breathe. Make sure you're doing things correctly. I know my arithmetic is my weak point. For you, maybe your algebra might be your weak point. Wherever you know that is, make sure that you take a moment and breathe. So 3/5. Okay, and finally we need to compute f of 2. That's 2 over 2 squared plus 1. That's 2/5, right? Close our parentheses, and there it is. There's your Riemann sum. We factored delta x out of each term just to make it look prettier, but that's it. So now if you want to know what this approximation is, or how good this approximation is, we can compute it explicitly and compare it to the 1/2 times the natural log of 5. So I've got a bunch of ratios over 5. Let's combine those first. So I've got 2, 3, 2 is 4, plus 3 is 7/5, plus 1/2. Okay, so this is, with 1/2 out front, we can write these as ratios over 10 if we like. So 7/5 is 14/10. And this guy would be 5/10, so we'll write it. Especially after I preached to you about taking time during your troubled spaces. So this is 19/10 times 1/2. Or 19/20 if you like. Yeah. Pretty close to 1. Now is 1/2 times the natural log of 5 especially close to 1? I don't know off the top of my head. But let's see what that is as a decimal. So Wolfram Alpha tells me that's about 0.8047. Okay, so not as good as our last approximation was, but still not bad. The key for all of these Riemann sum type problems, I feel, is to draw a picture that accurately represents the geometry of the problem you're fiddling with. And then just to take your time remembering your definitions. We didn't ever have to write down one of those scary capital sigma expressions because we knew what we were doing geometrically. You can do these from the general form, the sigmas and the n's, but you don't need to. Alright guys, so the next problem asks us to find the area under the graph of f of x equals 6x squared minus x cubed on the interval 0, 2. I'm not going to sketch the region here because you can see that this function, if you factor x squared out, is not 0 anywhere on that interval. So we're not going to play around with that. The answer will either come out to be positive if this thing were positive area, or negative if this thing were negative on this interval. Because it doesn't change sign, we know it doesn't change sign on that interval, I won't bother. So the task is just to compute the integral from 0 to 2 of 6x squared minus x cubed dx. And the method is just the power rule. So first we'll find antiderivatives for each of those. An antiderivative for x cubed is 1/3, or x squared is 1/3 x cubed. So that 6x squared will become 2x cubed. And this guy will become 1/4 x to the 4, and we need to evaluate between our endpoints 0 and 2. The lower limit is going to contribute nothing, because both of these are equal to 0 at 0. So we only need to worry about the upper limit, and this is 2 times 8 minus 1/4 times 16. 2 times 8 is 16, 1/4 times 16 is 4. So the area under the graph is 12 units squared. Okay guys, the 9th problem on part 2 of the final exam review comes with a lot of words, but what it says is dx dp is equal to 30 divided by the square root of 10 plus 0.6p, and we're told that p of 1,000 equals 10. In other words, at price $10 per unit, you will sell 1,000 units. So we're in that land of economics problems. We're asked to recover the revenue function, r, as a function of p. So let's go ahead and do that. Given that dx dp is equal to this, I know that up to a constant, x will be equal to the antiderivative of 30 divided by the square root of 10 plus 0.6 is 3/5. I'll write that as a fraction to make life nicer. dp, right? In order to kill the dp derivative, we integrate with respect to p. So we can bring the factor of 30 out and make a substitution. The substitution we want to make in this case is z equals 10 plus 3/5 p. So the stuff underneath that square root, because if that were just one thing, this would be easy. If we do that, then dz is equal to 3/5 dp. And so dp is equal to 5/3 dz. So I'll have my 30s out front. I've got 1 over the square root of z, 5/3 dp. Okay, so here's my substitution. We didn't have to change any limits of integration because this is a definite integral. So what else can we do? Well, we know 1 over z is z to the negative 1/2. I know I can bring my 5/3 out here, and that will become 50. And I'm left with the integral z to the negative 1/2 dz, which is, you always add 1 to the power and then divide by the new power, so that's going to be 2 times the square root of z, so this will be 100 square root of z plus some constant. Okay? Now we can go back to our original variables. So z is 10 plus 3/5 p, so this is 100 times the square root of 10 plus 3/5 p plus c. So we're on our way to finding x as a function of p, which will be useful if we want to write down the revenue function. Before we're able to proceed from here, we need to know what this constant c is, right? As in all these other problems. Thankfully, we've been given some information that will help us do that. We're told that p of 1,000 equals 10. This isn't how it's given to you in the problem, it's just a compact way to write it. In other words, x equals 1,000 corresponds to p equals 10. So if we plug those values in to find c, I'm going to erase this. So if we plug in x equals 1,000, then we get 1,000 is equal to 100 times the square root of 10 plus 3/5 of 10 plus a constant. So that's constant's what we're trying to figure out. Now, if you simplify under the square root, this becomes 6, so you get the square root of 16. So this is 100 times the square root of 16 is 4 plus c. So c is, 1,000, this is 1,000. So c is 600. Okay? So now we can write down x as a function of p. That is this guy. Okay, so x is equal to 100 times the square root of 10 plus 3/5 p plus 600. Now you know that the revenue function r, it's equal to x times p, right? So here I have x as a function of p. So you can see if I want to get r out, I take x of p and I just multiply it by p. So r is equal to p times x of p, which is equal to 100p times the square root 10 plus 3/5 p plus 600 p. And there you have it. Okay guys, in the 10th problem in part 2 of the MAC2233 online final exam review, we're asked to find the area bounded by the graph f of x equals 2 minus x on the interval 0, 4. This is very similar to a few other problems that we've done. The key is to sketch the region, or to observe that this thing changes sign on that interval and then just do it algebraically, but we'll sketch the region. So on 0, 4, what does 2 minus x look like? Well, 2 minus x is a line. It looks something like this. It's equal to 0 at 2. So on 0, 4, if you were to just integrate f of x across the whole thing, you're going to pick this up positive and this up negative. So if you want to measure that area accurately, you need to either use geometry, because these are triangles, or you can split the integral into two pieces. We're in a calculus class, so we'll split the integral into two pieces. So the area is equal to the integral from 0 to 2, f of x dx, minus the integral from 2 to 4, f of x dx. This minus being the negative one, we need to make sure this area isn't counted with negative weight in order to correct the natural negative weighting of the integral. F of x is 2 minus x. An antiderivative for 2 minus x is 2x minus x squared over 2. So we'll evaluate from 0 to 2. I'll use parentheses to make sure we keep everything contained safely. And we'll evaluate from 2 to 4 separately. Okay, at 0, these are both 0, so we don't have to worry about anything coming from there. At 2, this is 2 times 2 is 4, minus 2 squared is 4 over 2 is 2. Okay, so minus 0 from my upper limit, minus. Now if I plug in 4, I get 2 times 4 is 8, minus 4 squared is 16 over 2 is also 8. And from that, I must subtract what I get when I plug in the lower limit. This is 2 again, so this is going to be 4 minus 4 squared over 2. So that's everything. This first piece is 2, and then I'm going to subtract from that 0, and then here I've got another minus sign and another 2, so this piles up to 2. Write it like this way, minus negative 2, which is 4. If you compute each of these geometrically, you'll find that these both have equal area, and that's what we're seeing here. This guy's doubling the area of that. If you were to run the integral straight from 0 to 4, since, as we just observed, they're equal area, then these two would annihilate each other. The integral from 0 to 4 of this function is exactly 0. Okay guys, in the 11th problem, we're given the piecewise function f of x equals 3 for x less than or equal to 0, and the square root of 9 minus x squared if x is between 0 and 3. We're told to find the integral from negative 2 to 3 of f of x dx, and it's hinted at that we should use some geometry. So let's go ahead and take a look at this. We'll talk for a minute about what we can do. With these piecewise functions, it's nice to get a nice picture in our minds if we can. So if x is strictly less than 0, you know this thing is the constant function 3. So let's come 1, 2, 3. Even at 0, right? Because this is less than or equal to. So you can fill in and run all the way out there, no problem. And now what about the other piece? F of x equals square root of 9 minus x squared. If you haven't seen things like this at all in the past, then it might be a little bit foreign to you. So you know, the graph there should look like the graph of y equals the square root of 9 minus x squared, at least on this interval. And while that might not look familiar to you, I suspect that a slight rearrangement of it will. So if I square both sides and then add x squared, you get this, which you should recognize as a circle centered at 0, 0 with radius 3, right? Because 9 is 3 squared. So this is the general form for a circle centered at 0, 0 with radius 3. So you know it's going to be some subset of the graph here, right? So maybe if this is 1, 2, 3, yeah? So then the question is, if instead of taking this whole thing, right, which you know corresponds to the plus and minus square root, and I only look at the plus square root, which is what's always given if there's no sign in front of it, then you ask, well, what subset of the graph of the circle is this thing giving me? And the answer is because this is positive, right? I'm only going to get as outputs possible positive y values, and as x runs from 0 to 3, this takes on all the values between 0 and 3. So for x between negative 3 and 3, this is the graph of that function. for x just running from 0 to 3, this is the graph of that function. So it's not a semicircle. If you just look at this, then you get the upper semicircle. You get half of a semicircle. But then if you restrict the domain further, then you get a quarter of a circle. So the graph of our function, our piecewise function, and we stop right at 3, right? Okay, so that's filled in as well. Looks like that. I know I'm not an artist, just pretend that this is a circle. If we were to try to evaluate this with an integral, at first you might think it's not so bad. Clearly, if I want to evaluate -2 to 3, f of x dx, I need to split it according to the piecewise split, like we've done in some other problems. So I'd integrate from -2 up to 0, the constant function, 3 dx, and I'd add to that the integral from 0 to 3 of the square root of 9 minus x squared dx. Of course, you know how to do this one, and you might play with this for a while, but we don't actually have the tools at this point to handle that. There is a trick, you'll learn it pretty early in Calc 2, called trigonometric substitution, which will allow you to handle this and other integrals with things like this in the integrand. But right now, a regular U substitution isn't sufficient, at least not the normal way you think of it. If you were exceptionally clever, you might be able to come up with what is essentially the trig sub method on your own. But I won't bother you but I won't waste your time with that. You'll learn it in Calc 2. We were told to do this geometrically, so let's do it geometrically. We can decompose the region in question into two shapes that we know well. If I'm looking here at -2, then my region looks like this rectangle together with this portion of a circle. Now you know this radius. Sorry, that's ugly. You know this radius is 3. You know this height is 3. And you know this width is 2. So you can compute everything. The area of the rectangle is equal to 2 times 3. The area of the portion of a circle, if this wasn't such a neat division of the circle, you might have to remember how to find the area of a sector of a circle, but we don't even need to go that far. You know this is exactly 1/4 of that circle, so you take the area of the whole circle, which is pi times the radius squared, and you divide it by 4. Okay? So 9 pi over 4. You sum these two, you get the total area, which you know corresponds to that integral. Therefore, the integral from -2 to 3 of f of x dx is equal to 6 plus 9 pi over 4. Okay guys, the next problem tells us that the rate of change of some population that's being measured somewhere, dp dt, is equal to 50t minus 100t to the 3 halves. We're asked to find the net change in population over the first 4 years. Those are the years corresponding to t equals 0 to t equals 4. Since net change in population is given by just the difference, p of 4 minus p of 0, we know that what we ought to do is to integrate, because the fundamental theorem of calculus tells me that p of 4 minus p of 0 is equal to the integral from 0 to 4 of p primed of t dt. P primed is the same as dp dt. So this whole thing is equal to the integral from 0 to 4 of 50t minus 100t to the 3 halves dt. Each of those are power rule problems. So 50t, an antiderivative, is 50t squared over 2 minus 100 t to the 3 halves becomes t to the 5 halves, and we must divide by 5 halves. And then we need to evaluate this between 0 and 4. Now those can be simplified. 50 divided by 2 is 25. Minus, now I've got 100 divided by 5 halves. So that's 100 times 2/5. 100 divided by 5 is 20, times 2 is 40. So minus 40 t to the 5 halves. And again, evaluating between 0 and 4. All right. The lower limit contributes nothing, so we can just get this from the upper limit of 4. If we plug 4 in here, then I'll have 25 times 4 squared is just 25 times 16. And I'll subtract from that 40 times 4 to the 5 halves. 4 to the 5 halves isn't too bad. What is that? That's 2 to the 5th. That's 32. Okay, and now the arithmetic. Let's see, 25 times 16, every 4 of these we get 100. We've got 4 of those, so this is 400. Minus 40 times 32 is going to take just a second. This would be faster than me doing it myself. Maybe not. It's always a race. 1280. So 1280 is certainly larger than 400, so this net change is going to be in the downward direction. And we get 880, of course, 880. So this is negative 880. So that's it, that's our net change. We might want to pay attention to our units. Did they tell us this population is being measured in any interesting units? Population in thousands, yeah, right? So this is actually a loss of 880,000 whatevers over that amount of time. Okay, this next problem is a word problem. I've only written down the crucial information on the board, but it tells us that the price of a particular model of Toyota is increasing at the rate 3t over the square root of 3t squared plus 4. And they ask us to find the net change in the price from t equals 0 to t equals 2. Again, they told us that this is the rate of change of the price, so I've expressed that as ddt of the price or price prime. I didn't want to confuse it with the notations we have with little p's elsewhere. But in any case, you know that to find the net change, just like in the previous problem, you need to find out what the price is at t equals 2 and subtract from that the price at t equals 0. We don't have the price function explicitly, but the fundamental theorem of calculus gives us a great way to get precisely this difference. We know it's the integral, just like in the previous problem, in this case from 0 to 2, of the derivative of the price, which is this function here. So we have to integrate 3t over the square root of 3t squared plus 4 from 0 to 2 dt. This should look familiar. We've done a handful of similar problems, so if you make the substitution, z equals 3t squared plus 4, then dz is going to be 6t dt, which thankfully is a constant multiple of the derivative of the top. We're going to change our limits because we're making a substitution in a definite integral. So notice that when t is equal to 0, z is equal to 4. Similarly, when t is equal to 2, z is equal to 12, 14, 15, 16, 17, 12. Did we say that right? So at t equals 2, this is 3 times 2 squared is 12, plus 4 is 16. So 2 goes to 16. All right, remember, to get your new limits, just plug the old limits into the substitution. So at t equals 0, we know from our substitution z is 4, and similarly at t equals 2, z is 16. So the integral in question becomes the integral from 4 to 16. And how does our substitution fit? Well, the square root under the radicand down there is exactly z. Upstairs I had 3t. dz is equal to 6t dt. And so the t dt's go together, but 3 and 6 aren't identical. So one way of saying this is maybe that dz over 2 is equal to 3t dt. However you feel like doing it. Throughout this process I've been avoiding, throughout the whole review, I've been avoiding ever mixing variables in an expression with an integral and canceling. I know that's the way a lot of people learn, a lot of people are most comfortable. I'm trying to avoid the snafu of writing down something that doesn't exist or isn't well defined. But however you're comfortable sorting out with this substitution, or how these substitutions grind in general. We're going to get a factor of 1/2 is the take home when we replace dz by dt, or dt by dz. So this is our new integral. We can pull our 1/2 out. Now 1 over the square root of z is z to the negative 1/2. If you add 1 to that power, you get 1/2. If you divide by that power, you're multiplying by 2. It will cancel with the 1/2 out front. So this is just the square root of z evaluated between z equals 4 and z equals 16. So if you plug 16 in, you get 4. And if you plug 4 in, you get 2. So the net change there is 2. We want to be careful of our units. So we were told that the units here, we're measuring in thousands of dollars. So this is actually a net change of $2,000. I'll assume US dollars. Since it's positive, we know it's an increase. If it were negative, as in the previous problem, it would have been a decrease. Number 14 is a problem in several parts, so I will split these up. They're all finding areas, so we're going to be doing some integration, only now we're looking at areas between different graphs of different functions, or sometimes areas bounded by multiple, more than 2 functions. In this case, we're told to find the area between, or enclosed by, the graphs of f of x equals square root of x plus 1, g of x equals e to the minus x, and the relation x equals 1. So we can, as always, start by sketching these. Square root of x plus 1 is the regular square rooting function shifted to the left by 1. This graph looks like this. So this is f of x. G of x is e to the minus x, is e to the x, but reflected about the y-axis, so he comes close to 0 down here, and then takes off like a rocket as you go over that way. This is g. And the line x equals 1, let's say 1 is here, is a vertical line that looks like that. So the region in question is this shaded area. And you might ask, how do we do this? The trick here is going to be finding this x value, whatever that is, and we will integrate from there to 1, the function that dominates minus this guy, right? So upper minus lower from A to B works when your region has this shape. And I think for most of the problems you guys are going to encounter in this class, that will work as well. So let's do it. We need to find this intersection point. We need to find where f of x is equal to g of x. That'll happen if and only if the square root of x plus 1 is equal to e to the minus x. If we square both sides, then you can see that that's the same as doing a handful of things. I just see now that I've drawn my picture on. You can actually solve this by inspection, right? So without thinking at all, notice that x equals 0 actually solves. So my y-axis should have been right here. I sketched this freehand, of course, without plotting any points or anything. So it turns out that this is the magic spot. If you wanted to solve it properly or without going by inspection, we may have a way to do that. So let's try squaring both sides. So then we get, it's not nice looking, right? So I think no matter what you do, this is going to have to be something where you solve. Oh, no. Yeah. Right, so if you take a natural log to free this guy, then this will be trapped in a log. Conversely, if you tried to exponentiate, this will become a super exponential. So solving by inspection seems to be the way to go there. I don't think any of these equivalent statements are going to be any less opaque than the original. So you solve this equation by inspection, noting that x equals 0 is the only solution. So we'll be integrating from 0 to 1, the upper function minus the lower function. So the area, integral from 0 to 1. Now my upper function here, throughout this whole region, is f, right? They never switch. So I'll have f of x minus g of x dx. If they were to cross again, then we might have to split the integral up into separate cases. But since these guys do not, we can just go ahead and crunch this out. F of x is the square root of x plus 1. G of x is e to the minus x. We can handle each of those separately. this guy will benefit from a little substitution if you don't see it already. Letting z, or we've used z the last few times, let's use u equals x plus 1. du is still just dx. My limits change from 0 goes to 1, 1 goes to 2. So that's my substitution that I'm going to employ here. So I get the integral from 1 to 2 of the square root of u du. This guy falls into that class of integrals we had over here earlier, if you remember. E to the ax dx, that always integrates e to the ax over a plus a constant. Remember, I mentioned that these come up so frequently that we should be familiar with them directly. We shouldn't have to make the substitution u equals negative x. You could say the same about this. I think you get used to these a little later than you get used to these. So this guy has this as antiderivative, e to the negative x divided by negative 1. So this minus is going to become a plus. I have e to the negative x. And here I'm going to evaluate 0 to 1. Now the square root of u is u to the 1/2. We know that that has as an antiderivative 2/3 u to the 3/2. And he needs to evaluate it between 1 and 2. Okay. If we evaluate this guy at 2, we get 2/3 times 2 to the 3/2, which is 8. If I evaluate at 1, I just get 2/3. E to the negative 1 is just e to the negative 1. E to the 0 is 1. So this is what we get. Now you can clean this up as much as you like. Let's see, so this is 2/3 times 7, so that's 14/3. And then I can bring this minus 1 over here, that's minus 3/3, plus e to the negative 1. So altogether, it looks like we're going to get 11/3 plus 1 over e, or e to the negative 1. And that is, of course, measured in units squared, right? All of these areas. But that's it. Okay guys, we're looking at part B of problem 14 in the final exam review for UF Online students, the class MAC2233. Just as in part A, we're looking at areas of regions bounded by curves, and we're hoping to find these using some tricks, geometry, integration. In this case, we're looking at the area that's contained in the region bounded by the curves f of x equals 2x minus 1, g of x equals x squared minus 4. So as always, it's useful to graph these. Now you know what g of x looks like. I'll try to draw a pleasant looking picture. And you know what 2x minus 1 looks like, approximately, right? Okay. I reserve the right to say these are scaled so that I can make everything fit nicely. But this is what's going to happen, right? This is a line with y-intercept negative 1 and slope 2. And this is a parabola opening upwards with roots at negative 2 and 2. Its min is down here at negative 4. So we know that this is approximately the shape. If we want to find the area of the region enclosed by those two, then it's imperative that we find where they intersect, right? As in the previous problem, we're going to integrate the upper minus the lower function from a to b, where a and b are the x values that allow you to sweep that region. Sometimes these problems can be a little bit complicated, but for the most part, ours will be relatively simple in this class. So I need to find out the two places where this line meets this function. And in order to do that, as previously, we set f of x equal to g of x to find the intersection. Okay, we're expecting two solutions, but we've got 2x minus 1 equals x squared minus 4. We can pull a bunch of stuff to this side, so I'll have 0 equals x squared minus 2x plus 1 minus 4. Okay. I wrote it that way because that's suggestive of completing the square. So this is x minus 1 squared minus 4. So if that's equal to 0, then 4 is equal to x minus 1 squared, which will have the two solutions that come from 2 equals x minus 1 and negative 2 equals x minus 1. Therefore, x is equal to 3, and the other solution is x equals negative 1. Okay? So just happened to work out nicely completing the square without thinking too hard. So this guy is negative 1, and this guy is 3. Therefore, to find the shaded area, we need to integrate from negative 1 to 3, the upper function, which is f, minus the lower function, which is g. Okay? So, let's give ourselves some space. The integral from negative 1 to 3 of f of x minus g of x dx is equal to the integral from negative 1 to 3 of, actually this difference, right? It's the same one, but we'll play nice. 2x minus 1 minus x squared minus 4, right? F of x minus g of x dx. Continuing on this way, that's negative 1 to 3. Right, yeah, not g minus f, f minus g. So we'll have negative x squared. And what about the coefficient for x? Looks like it's just going to be 2x. What about constant terms? I've got negative 1 minus negative 4. Looks to me like a 3. Okay. So that's what I need to find an antiderivative for. Again, the power rule does all the work for us. So this guy is going to become negative 1/3 x cubed. And I'll have plus x squared over 2, but the 2's cancel. And then plus 3x. Okay, and this needs to be evaluated between negative 1 and 3. To evaluate at 3, I mean, we just plug in now. So 3 cubed is 27. Divided by 3, though, is 9. So this is minus 9 plus 9 plus 9 minus, so I should use some parentheses here. You always use parentheses very carefully. Minus what I get when I plug in negative 1. Negative 1 cubed is negative 1, so this will become positive 1/3 plus 1 minus 3. Okay? So funny that we got all of those 9s out of the upper limit, but that's how it goes. So we have 9 minus 1/3, and then 1 minus 3 is negative 2 plus 2. Okay? You can write this however you want. I guess the nice thing to do would be to write it as 1/3. So 9 and 2 is 11. 11 as a ratio over 3 is 33. Minus 1/3 is 32/3, which cannot be simplified. Okay, good. So that's it. 32/3 units squared is the area contained in this region. Next we'll do part C. All right, guys, we're going to tackle the last part, part C of problem 14 in this review. It's the same stuff as the previous two parts. We're given two curves and we're asked to find the area of the region bounded between them. In this case, the curves are a little more complicated. They're cubic polynomials, and while we can graph those, we can graph them with some accuracy considering what you've learned in Calc 1. I'm going to show you a slightly different approach. So you know that if we look at an arbitrary region for a second, two curves, say something like this, let me label this guy as F and this guy as G. If I were to look between here and here and ask for this area, you would integrate F minus G. But if I wanted this area, you would integrate G minus F. So if you know that the regions of these, the regions whose area you're trying to calculate are coming from shapes like this, where curves are intersecting, creating bounded regions, it's sufficient to set up your integral. You don't have to sketch the region. You just have to know which function dominates which other function on the intervals in question. The intervals come from the points of intersection, and so we just have to figure out where each function is larger in each of these intervals. You could have more points, you could have fewer points, but let's get to it. So first we're going to find the intersection points. Those will be where f minus g is equal to 0. F minus g is 2x cubed minus x cubed is x cubed. 0x squared minus 2x squared is minus 2x squared. Minus 6x minus 2x is minus 8x. And this is equal to x times x squared minus 2x minus 8, which is equal to x times, let's see, x minus 4 times x plus 2, right? Okay. So our intersection points are x equals -2, 0, and 4. You can put those on a number line. And just as in the general example I had up a second ago, I know that the regions in question are between here and here and here and here, right? The only way to get a bounded area by these two curves is for them to intersect at both sides. So I need to find out which one's larger, f or g, between -2 and 0. And the same question, which one's larger, f or g, between 0 and 4? One way to do that is to just know the sign of the function I've been playing with so far, f minus g. If f minus g is positive, then f is bigger. If f minus g is negative, then g is bigger. So let's see if we can fill in each of these regions. One trick for this is knowing what we know about end behavior and multiplicities of polynomials. I know that this is a cubic function with a positive coefficient, positive leading coefficient. So as x runs off to -infinity, so will that cubic function. It's dominated by that. So if I walk out to the left of -2, I expect this to be negative. I know it is negative. As we jump over the 0 of multiplicity 1 at -2, I am certain that it will change sign. Same is true at the 0 here, from multiplicity 1 at 0, and same is true over here. Now we only really care about these two, but I just want to, for completeness, to fill those in. So, the area in question is equal to the integral from -2 to 0 of f minus g plus the integral from 0 to 4 of g minus f. Okay? We'll compute each of those. F minus g is this thing, so that's x cubed minus 2x squared minus 8x dx plus 0 to 4. G minus f is just -1 times this, so that's -x cubed plus 2x squared plus 8x dx. Very easy to make a little sign error here, so just take your time, make sure everything's correct. All right, so on 0 to 4, I know g is larger because f minus g is negative, so I take g minus f. G minus f is negative f minus g, is -x cubed plus 2x squared plus 8x, good. And on -2, 0, I know f is larger because f minus g is positive, so I just have to copy him down. Okay. Now we write down our antiderivatives. Let's continue off to this way so we can conserve some space. So this first fellow, antiderivative for x cubed is x to the 4th over 4. And then minus 2x squared, it's going to be minus 2 over 3 x cubed right? Because x squared is 1/3 x cubed, has as its antiderivative 1/3 x cubed. And then minus 8x is going to become minus 8x squared divided by 2, so minus 4x squared. And this needs to be evaluated between -2 and 0. My other piece is just these guys negative evaluated between the other endpoints. So it will be negative x to the 4th over 4 plus 2/3 x cubed plus 4x squared, evaluated between 0 and 4. Okay? I get these antiderivatives as being the negatives of these because this whole function is the negative of this, and the linearity of the integral plays nice. All right, so now we need to evaluate each of these pieces. If I plug 0 in here, I don't get anything at all, right? If I plug 0 in here, I get 0, right? Because each of those is 0. So this first piece is 0 minus. Now what do I get if I plug in -2? I'll have -2 to the 4th over 4, which is the same as 2 to the 4th over 4. So that's not the nicest way to say that, I guess. It's just that 2 to the 4th is 16 divided by 4 is 4, right? Then I'll have minus 2/3 times -2 cubed. Okay, so -2 cubed is -8, so this will become positive, and then 8 times 2 is 16. So this becomes positive 16/3. Okay, and then I've got minus 4 times -2 squared. -2 squared is 4 times 4 is 16. And that's everything from the first integral. Right? Did I miss anything? I don't think so. That's positive 8/3. Yeah, good, okay. So we'll close that off. Now I need to add to that what I get from evaluating this guy. Now here the lower limit contributes 0, so I won't have to worry about him, but we do have to worry about the upper limit. So if I plug 4 in here, then I'll have 4 raised to the 4th power divided by 4. That's 4 raised to the 3rd power. That's 4 times 4 times 4 is 16 times 4 is 64. So I've got my negative 64 plus 2/3 times 4 cubed. So 4 cubed again is 64. Times 2 is 128. So I've got 128/3. And now I've got plus 4 times 4 squared is 4 cubed, so plus 64. Now when I plug in my lower limit 0, I get nothing, I get 0 out, so that's fine. So the second integral is 128/3. The first integral demands to be simplified a little bit, but not too much. So here, I've got 4 minus 16 is -12, times -1 is 12, plus 16 over 3, plus 128 over 3. I'm sorry, no. This should be minus, right? So 16 plus 4, -12, negative, yeah. Okay. So this is the contribution from my first integral. This is the contribution from my second integral. We should make sure each of these is positive because each of these is measuring an area. If one of these were to come out to be negative, either we've made a mistake somewhere in our integration, our evaluation, or all the way back up there in our number line, leading us to set the integral up incorrectly. But 16 over 3 is certainly less than 12, And 128 over 3 is clearly positive, so that's your gamma. That's the area. We can combine these if we like. All his ratios over 3, so you've got 128 minus 16, that's 122, 112 over 3, right? So we have 12 plus 112 over 3, looks like. And then if you wanted to write this as a ratio over 3, what is that? 36. And then 36 and 112. Let's see, so this is 118. So that's 128. 118 plus 30 is 148, right? So it looks like 148 thirds is our answer. Okay guys, for the last problem on this review, we're given demand and supply functions. Demand is d of q is 11 minus 3/10 q squared, and s of q, the supply function, is 1/10 q squared plus 1. We're told to find consumer and producer surpluses at the equilibrium point. So first we need to find the equilibrium point. That's where these two are equal. So we'll set, my marker's starting to die, d of q equal to s of q. And that is, if 11 minus 3 over 10 q squared is equal to 1 over 10 q squared plus 1. This is clearly equivalent to 0 being equal to 4/10 q squared minus 10. And that's true, provided, we can do this the silly way, right? 10 is equal to 4 over 10 q squared, which is itself equivalent to saying q is plus or minus, let's see, well, it would be the square root of 100 over 4, so that's 10 halves. All right. Now we're interested in positive q. Q's measuring something, measuring quantities, so we're going to throw away the negative solution. And then the equilibrium point, we've got this q value. These two are equal there, so you can plug this back into either of those to get your equilibrium point. So this tells us that the equilibrium point is given by 10 halves, comma, say q of 10 halves, or sorry, say d of 10 halves. Maybe s is nicer, it doesn't really matter. So let's go with s here. If I plug 10 halves in here, yeah, let's do it here. S of 10 halves is 1/10 times 10 halves squared plus 1. That's 10 over 4. Plus 1, that's 14 over 4. Okay, so that's our equilibrium point. 14 over 4, which is the same as 7 halves. Now you've got a formula for your consumer and producer surplus, which I don't have memorized, so I will write down here. Your consumer surplus is given by d of q, the integral from 0, so this is, I should say, this is called q star. So you want to integrate from 0 up to q star, d of q dq minus p star q star. So d of q is this. Integrate dq, and then we'll subtract off the product of these two. So this is sometimes also called p star. Okay? So that is 70/4. So what we really need to do is compute this integral. So this is our consumer surplus. An antiderivative here, taken with respect to q, is going to be 11q minus 3/10 q cubed over 3. This is to be evaluated between 0 and q star. I might as well write in what q star is, right? Q star is 10/2, or, that's silly, why would I write it like that? Let's just call that 5. Okay? And we've got to subtract this quantity off as well. All right. So nothing in here is going to come from this lower limit because these both have q's in them, so the upper limit is the only contributing factor. 11 times 5 is 55, minus these guys cancel. 5 cubed is 125, so 125 over 10. And then minus this. Okay, we can write 55 as a ratio over 10 is 550. So this is 550 minus 125 divided by 10 plus 70 over 4. So that's 525, 425 over 10 plus 70 over 4. And you can write those with a common denominator if you like. I don't particularly care to. That's your answer. Now to get our producer surplus, we find a better marker. Good. And there's a similar integral formula for that. So the producer's surplus is given by p star q star minus the integral from 0 up to q star of s of q dq. All right, p star q star is still just this number. Minus the integral from 0 up to q star is 5. S of q is 1/10 q squared plus 1. Taken with respect to q. So this is 70 over 4 minus, now we can again apply the power rule here. Integral of q squared is 1/3 q cubed, so this will become 1 over 30 q cubed plus q, evaluated from 0 to 5. Again, the lower limit contributes nothing, the upper limit gives us everything, so we'll have 125 over 30 plus 5. Now 125 isn't divisible by 30, but it is divisible by 5. So we can reduce this to, let's see, 25 over 6 plus 5. And then we'll leave it at just 2 ratios. So this is 70 over 4 minus, what do we have here? If I want to write 5 as a ratio over 6, it's 30, right? I just used that. So this is 30 plus 25 is 55 over 6. Okay, so that's it. Your producer surplus is 70/4 minus 55 over 6, and your consumer surplus is 425/10 plus 70 over 4. That does it for this review, guys. I am going to record some of the more challenging problems from the practice test and try to get those out to you as soon as possible. I know UF Online students don't have all the same resources that students who take these classes on campus do. So at the Broward Teaching Center, we're doing our very best to get you everything we possibly can. That's it. Until next time.
The Teaching Center, UF's Learning Resource Center.